Great. It looks like we have most of the people in from the waiting room, so I won't keep us for too long before we get to Claire's talk. Welcome everyone to our second Curiosity Lab, Triples, Triangles, and Clay Tablets, the story of the Pythagorean Theorem. Looking forward to the talk today with Clare Hamblen. She is an alum from 2012. She's also a mentor with our mentor program, which is now called College Link. And we are excited to have her. And I will just pass it right over. Actually, one second. Just a little housekeeping. We do have the chat open, so feel free to drop any questions in that chat. And please keep yourself on mute for the majority of the presentation. We will have some Q&A at the end where anyone can come off mute and ask a question. All right, Claire, take it away.
I first have to figure out, I'm getting like a chime every time someone joins in the waiting room. So I don't know how to silence that.
I wasn't sure if that was for me only. So let me see if I can
Perfect.
set that as well.
We'll figure it out for you, Claire.
Okay, thank you. Okay, let me set up my screen. Let's see. Okay, I got that. I got that. I got that. And then now I'm doing this. Okay, can we all see my screen here? Great. Okay, so first of all, I'm Claire. I'm an SSP alum from 2012, back when the program was just astrophysics. And these days, I earn my living teaching math. I work for myself as a math tutor. And, over the process of doing that, I definitely have taught a lot of lessons on the Pythagorean Theorem. And eventually I kind of realized that, the topic, not only does that topic have a lot of fascinating history, but actually teaching this, the Pythagorean Theorem along with its history is a really great way to engage all my students and all my learners. And so this talk kind of was developed. I developed this from a lesson that I teach with my grade level kiddos. And then I kind of just threw in some other aspects to this history. As we're tracing the historical development, my goal here is really to illuminate kind of a deeper meaning of the theorem and sort of to explore how meaning is developed in mathematics across culture and over time, kind of taking a fresh look at a familiar result. Possibly the most famous theorem in math is the Pythagorean Theorem. And it says that in a right-angled triangle, the square of the hypotenuse equals the sum of the squares of the legs. And we typically, represent that with this equation. And we can visualize this phrase, like this. So the idea being, if I construct a square, both side lengths being the same, off of each leg of the triangle, the combined area of those squares will equal the area off of that hypotenuse there. And when you're teaching this topic, again, whether it's in middle school, high school, college, some of the questions that you can ask, commonly relate to finding lengths of a missing side, although of course there's other things you can do with this. And in doing so, you're typically, you're plugging numbers into this equation and calculating some missing value. The theorem was named for Pythagoras. So the natural question to ask is, who was that? So Pythagoras is an interesting figure because no documents survive, that were contemporary to his life. So the only biographical information that we have about him comes from stories and legends. We believe he was born in around 580 BC on an island, Greek island, and he traveled to the mainland to learn mathematics from Thales. Now, Thales is considered to be the founder of Greek mathematics. He is the one who gave us the deductive method, which really, is deeply influential in mathematics for millennia and still is. Eventually, Pythagoras settled down, and by 540, he had founded a school that we know today as the Pythagoreans. The Pythagoreans, they were interesting today, and they were interesting even to their contemporaries in ancient Greece. They had a belief that mathematics, could unify religion, science, and philosophy. So they were more than just mathematicians. Their motto was all is number. They actually gave us the word mathematics. So from them, we have the meaning of the word mathematics, which just means that which is learned. And, in some ways, the Pythagoreans were, they had this idea that natural phenomena could be explained by uncovering hidden mathematical relationships. One example is in the harmonics of a vibrating string. Ratios of different lengths of string are what result in the sound of different octaves. So they were mathematicians, but really, am I back? Okay. So they were mathematicians, but more than that, they were aiming to kind of unify these different domains that all had this, around the natural universe. They had a strict code of secrecy, and actually, interestingly, an equally strict code of vegetarianism. And the secrecy code meant that most of the results attributed to the school are attributed collectively. The identity of an individual discoverer was not revealed to outsiders. So these days, we generally don't know who specifically among the Pythagoreans is responsible for what, but we know collectively some of the math that they did. So, the theorem is named for Pythagoras. Did he discover it? Does it come from him? The answer to that question is a little more complicated than you might think, but to start with, the theorem does appear across cultures, as early as 1800 BC, so over 1,000 years before, in Babylon, also in China and in India, and in all these places, geographical places, it is believed that the theorem was discovered in one form or another independently. So it wasn't that, there was sort of cross-pollination happening among these mathematicians. We believe that each of these mathematical cultures kind of engaged with the theorem, discovered it kind of independently. We'll focus on the theorem as it emerges first from Babylon and then into Greece. And again, this idea of historical development has this dual meaning. On the one hand, its appearance in human history. On the other hand, the emergence of mathematical meaning over time. And really, what I hope to do in this talk is to kind of help you set aside that modern understanding of the theorem and look at it with fresh eyes. One perspective to think about is the theorem has this dual nature. On the one hand, it's a geometric relationship. It says something about the side lengths of right-angled triangles. On the other hand, it's an arithmetic relationship. It's about three numbers that satisfy some particular equation. And numbers with that relationship are called Pythagorean triples. It seems that actually these two relationships, geometric and arithmetic, they weren't always understood together. Specifically, the arithmetic relationship was the one that ancient cultures discovered or emphasized much before the geometric application. One reason for that, possibly, is that in ancient mathematics, geometry and arithmetic were actually generally kept kind of siloed from each other. They weren't really perceived to be in harmony. And again, to a modern audience, like to us today, that's strange. We are so used to, doing calculations with numbers to answer questions about shapes and to use shapes to visualize calculations and so on. But to the ancients, these two were not, these were not in harmony. That's more than just a quirk. It actually reflects something kind of important and maybe deep mathematically. Arithmetic is about numbers and counting processes. Fundamentally, arithmetic is discrete, which is a synonym for digital referring to the digits on your fingers. So you're thinking about enumerating quantities. On the other hand, geometry is visual. It deals with things that are measurable and mostly can be explored with constructions. And the objects that we study in geometry are continuous, lines, curves, and surfaces. So very different from the discrete numeric quantities in arithmetic. And here I have a nice quote. This is a phenomenal volume of the history of math that I sourced a lot throughout this talk. On the one hand, facts of arithmetic are clearly outcomes of counting processes. And actually, you would not a priori expect them to have any deeper meaning. On the other hand, when it comes to the continuous objects that we deal with in geometry, continuous objects cannot be built by discrete processes, at least not in a simple way. And one expects to visually see geometric facts rather than calculate them. So all of this is to say there's quite a deep tension between these two domains, especially if you are an ancient mathematician. These two were not always linked, and certainly not the way that they are today. Today we have a lot of linkages that sort of articulate arithmetic in context of geometry and vice versa. And so what this means is maybe we have a truer, deeper meaning of the Pythagorean theorem to use as we go through this talk. The Pythagorean theorem is the mathematical concept that arithmetic facts can have a geometric realization into shapes. It is a bridge, and probably the oldest bridge between these two domains. And so what I want you to take with you as we come into our next section is really thinking from the perspective of that ancient mathematician, one who does not have the linkages that we have today, the Pythagorean theorem being the first one. What we're today going to be building up towards is building this bridge ourselves in the form of the Pythagorean theorem. In this section, we'll talk almost none about shapes, but quite a lot about numbers, and also through the context of the clay tablet that's in the title of this talk. So I have to define a Pythagorean triple for you. I kind of did this before, but it is a set of three whole numbers which satisfy this particular numeric relationship. This is a type of Diophantine equation, and I say that just to illustrate that this is actually an intrinsically interesting question on its own, even without the application, the visualization into geometry. Exploring patterns within Pythagorean triples, finding them, working with them is itself a very rich and deep subject. Now, I want to call your attention to a practical thing that comes up when you're teaching about Pythagorean triples. The definition is limited to whole numbers, and not just any whole numbers. Here are two of the kinds of questions that we can ask learners of mathematics when we're on this subject. We can ask them to find the third number in a triple. So I give you two numbers and you calculate the third, or I can ask you to verify, if I give you three numbers, are they in a Pythagorean triple? And the pitfall for the teacher is that if you are not careful, you may inadvertently choose whole numbers. So you might think, okay, whole numbers, I'm in the clear, but you can choose whole numbers where the result of the calculation with a squared plus b squared equals c squared is itself not a whole number. In this example, we calculate, 17 squared minus 10 squared from the smallest and greatest values in the triple, and you would arrive that the third value, that leg, would be the square root of 189, which is an irreducible radical, and has this, infinite non-repeating decimal expression. This is the kind of thing that when you're teaching the subject, you got to be really careful not to pick, you got to pick nice numbers, because otherwise you will write problems that are sort of nonsense for your learners, because a Pythagorean triple is a set of whole numbers. Put a pin in this. This is gonna come up again later. Pythagorean triples are very ancient. How ancient, you ask? I'm so glad you asked. This is an image of a clay tablet, and this tablet is almost 4,000 years old. It's called Plimpton 322. It was found in modern-day Iraq, near an ancient Babylonian city. We believe that it was authored in around 1800 BC. As with all Babylonian tablets, it's written in cuneiform. Now, when you're reading this, know that cuneiform is read from the left to the right and from the top to the bottom, just like in English. It is organized into columns and to rows. You should see that the sides are mostly smooth, with the specific exception of this jagged edge over here on the left. Probably that left-hand portion broke off at some point. And because of how cuneiform is read and written, just like English, probably that's what the author was writing down first. So they started here. Essentially, we're missing sort of the beginning. We have the end, the middle and the end of the tablet, but not the beginning. Here's a color picture. We're mostly using the black and white one because it's so much clearer. The tablet was obtained by George Plimpton, not a mathematician. I think he was like a publisher, from an archaeological dealer in the 20s. In the 40s, it was obtained. I think when he died, he bequeathed his collection to, I think, Columbia, and it was analyzed by mathematicians for the first time in the 1940s. We are going to retrace a lot of that analysis ourselves. So we're going to go through a real translation of what this means. I told you that it's written in columns and rows, and it has 5 visible columns. Remember, we can't see what was also over here, and 15 visible rows, which are here. So you can see we got one really big column here and then 4 others. I really want you to remember that at this moment, like for the next, I don't know, looking at the next 5 slides, we really have no idea about anything that's coming up here. So keep that in mind when we're kind of trying to piece together what could be meant here, that the author, from our perspective, we have incomplete information. Something I do love that I find like very human about this tablet is it has headers. It has labels for each column. And anyone, thinking all SSP students right now, or anyone who's organized data in a tabular format, we have it drilled into us that your data has to have labels. You need row and column headers. And that's not a new idea, apparently. 4,000 years ago, the ancient Babylonians felt the same way. So this column's got, the tablet not only has the columns and the row organization, but they labeled everything very neatly. So we're going to go through a translation. Of course, these are cuneiform characters. We'll start over here in column 5. So column 5, actually, when you just go through these, cuneiform is written by composing multiple strokes. I took this slide out, but the values here, the symbols here in column 5 are actually just the numbers that refer to the row number that they are in. So this is essentially just a numeric label for which row you are in, okay? Column 4 contains this symbol, and that symbol is repeated all throughout the entire column. It's the same symbol in every single row. And this symbol translates into the word number. So taken together, columns 4 and 5 are just the phrase number 1, number 4, number 10. Okay? We're going to now come over to columns 2 and 3 and start there with the headings. The translation of the heading in column 2 is the word width. The translation of the heading in column 3 is the word diagonal. Here is the only mention of triangles in this whole section. Those sure seem like some triangle words to me. Those should make you think of triangles. When we translate the numbers in each column into their base 60, let me say this differently. When we translate those numbers, these characters first into numbers, you see that they are numbers, that's what I'm trying to say. Now, the Babylonians used a base 60 number system, so these don't look like our, base 10 numbers, but we can translate those. I just couldn't resist showing you a little of the work because, again, what I love about this is, there is a grade level standard. I have to check it. I think it's 2nd or 3rd grade. It's writing numbers in expanded form. So, for example, 123, that's 1 times 100, 2 times 10, 3 times 1. The meaning of our base 10 number system is that, we count up from 1 up to 10, and then those 10 units become sort of a bundle. And then we, count in multiples of 10. We go up to, 10 tens and so on. And that defines our place value. The Babylonians did the same thing, but rather than counting up to 10, they counted up to 60. That number might seem random, but actually it's not. And we're not going to go into any of the interesting things about base 60, but you can sort of follow the same expanded form calculation that 2nd and 3rd graders do with base 60. So here, this is 160 and 59 ones, which equals 119. This is 41 ones, 16 60s, and then one amount of 60 60s. And when you calculate that, you get 4,601. And if you do that in the entire tablet, this slide now shows you the decimal, the base 10 values, okay? So far, what we've established is the headings. The headings are the words width, diagonal in columns 2 and 3. In column 4 and 5, we've got the phrase line, and then a number. Column 4 and 5 is just sort of a row number like label. And then columns 2 and 3 show these values. We're not going to do much with column 1, so leave that aside. Believe it or not, these are a partial list of Pythagorean triples. Remember, this tablet dates back to 1800 BC, so 1300 years before Pythagoras lived and had even learned math yet. So, how do we know? How do we know? Because we only have 2 of 3 values. Right? So how do we know that these really are Pythagorean triples? Well, I'm going to show you. Here's a shorter list just of 7 of the values. And, if we use the language, the width and the diagonal, and we use that in the Pythagorean equation here, we can do so and calculate the values that would be predicted as the missing in the triple. In the first row, for example, using 119 as the width and 169 as the hypotenuse, then we can calculate that L would be equal to 120. That's first of all, those 3 numbers, 119, 120, and 169, those are a Pythagorean triple. But maybe what's more significant is that, as we mentioned earlier, if you are randomly collecting whole numbers, using the Pythagorean equation on them will not necessarily result in an integer solution. This is I'll just take you back. This is what I showed you here. If you're not careful in plugging numbers in to that Pythagorean theorem equation, even if you start with whole numbers, you might get a value which does not complete the set of a triple. What's exciting is that when you just try out the Pythagorean theorem in every row, and I'm only showing you 7 here, but if you try it in every row, every single time you calculate that the missing value is a whole number. And I have to emphasize it is almost impossible that a list of numbers could be collected, that these numbers could have been collected for any other reason than that they are members of a Pythagorean triple. If there was any other kind of numeric relationship that the author had in mind in choosing these numbers, then you would never expect that every single one of them works in the Pythagorean theorem equation. So the fact that all of these numbers actually work is extraordinary, and it means that there's really no other reason for writing down, gathering up all together these specific numbers. Let me go back. These specific numbers couldn't have no other pattern that connects them, really, and it's just enormously unlikely that if they had been gathered for some other reason that they would result in an integer solution with the Pythagorean equation. So all this is to say, it's just extraordinarily unlikely that we are looking at anything other than a list of Pythagorean triples. To me, this is just a huge wow moment, right? Where we started with this tablet, dissecting it from its cuneiform, first into base 60 and then into base 10. This is the complete list. Here's all 15 pairs of values. And with all of them, when you apply this relationship, think of yourself as just trying it out. Well, I wonder if the values that we translated work with this relationship, because that'd be pretty amazing. In fact, they do. Every single one of them. The next question that we're going to work on here is who wrote this? We at this point, you should be hopefully pretty convinced that we are looking at a partial list of Pythagorean triples. The question now is who wrote this tablet? The first interesting thing here is the tablet is formatted like an administrative document and not a mathematical one. There are actually a few errors in the original tablet, and I corrected those errors in the translation that I showed. What's important is those errors are not truly mathematical mistakes, but they're errors related to copying and to doing math by hand. If we have time at the end, I I took these out. I have some slides where I can show you those mistakes, but it literally is like writing an 8 where you meant to write a 9, and you divided by 2 where you meant to multiply by 2. So they're very innocent mistakes, and they do not give us any reason to doubt that there's a mathematical that the mathematical relationship here is the Pythagorean triples. It is that relationship, and the errors are just sort of practical things someone was writing, by hand. All this is to say, this is probably not the work of a professional mathematician. So, whose work is it? In Old Babylon, that was a society with a tremendous need for scribes. There were a lot of scribes in Old Babylon, and then schools to educate those scribes. Today we are aware, we've discovered over 500,000 clay tablets, with writing on them from Old Babylon. And since at least 2000 BC, mathematics was taught in Babylonian scribal schools. Scribes were educated very broadly, so they were not just limited to professionally useful skills. And I have actually a really interesting citation here. This is from Eleanor Robeson, who's one of the leading scholars on Plimpton 322. And according to her, she thinks that almost all of the the tablets and the artifacts we have from Old Babylon, she thinks we should interpret almost all of those as the products of schools and scribal training contexts. They're not professional mathematical works. They come from academic, scholastic contexts. So all this is to say, Plimpton 322 is probably a teacher's aid. Because of the format. It's an administrative document, not a mathematical one. Because of these innocent little mistakes. I mean, I'm thinking about everyone on the SSP campuses who's grading work and it's late and your eyes are blurry and you write something down wrong. And it's not because it's a genuine error, it's a little typo, okay? We do have some known historical context. We know that in Old Babylon, there was there were scholastic materials being produced in the form of tablets, and particularly mathematical ones. The other column, which we did not translate, kind of shows some scratch work, some intermediate calculations, the kind of thing that you would include if you were showing your students what to do, step by step in an example. There's also the question of those nice round integers. So let me take you back. Where did I put it? It was here. Here are all these final values that we calculate for the missing leg using, the Pythagorean equation on the two known values. All of these are much rounder, nicer values. 120 versus 119, 169. 4800 versus 4601, 6649. 600, 481, 769. The overall impression is that this was, a teacher kind of working on creating practice problems for their students or for themselves. And, these nice round integers answer this practical problem that comes up when you're teaching the subject. When you're teaching the subject, if you are not careful, you will pick whole numbers that do not have that do not themselves yield integer whole number solutions. So the author of Plimpton 322 was mindful of that. They carefully chose nice round values, not only to use, but to yield as a solution. And in all this together means that the author had to have quite a lot of knowledge about the Pythagorean theorem while not being a professional mathematician and while creating this to use in a school context. One takeaway here is that, really nothing has changed in 4,000 years. We're assigning the same math homework today that we were in 1800 BC. And, I can say that this is something, this concept here, like this takeaway is something I love to, a reason why I love to teach my students, my grade level students in 8th grade in geometry who are learning about this. The idea that, somebody else, someone in ancient Babylon 4,000 years ago was doing the same calculation for their homework that you're doing, it tends to spark a lot of interest. And even if, even with my students, if we omit some of the technical details or, we kind of streamline the presentation, this concept that, they are doing real math ancient math, important math, and that there's kind of this thread of shared humanity here. I mean, it just really sparks a lot of curiosity, and for me, I tend to see a lot of really high engagement after teaching, the historical context, because we'll do this and then we'll dive back into, okay, let's act like a Babylonian student and do some more homework, and it's just great for students have that wonder, the same that I have. So clearly, Pythagorean triples were well understood long before Pythagoras ever lived. And when I say well understood, I mean they were common enough and well understood enough to be taught in schools and assigned as math homework. Now, the language in the headers, width and diagonal, does suggest awareness of the geometric significance of these triples. However, thinking about what else we know of Babylonian mathematics from the era, we do think that they primarily were interested in the arithmetic relationship. Perhaps more interesting than the question of who first, was it Pythagoras first or not? More interesting than that comes if we take another look at what the numbers are. So again, W and D, those are the values that we translated from the tablet. L, those are the values that we calculated. And again, the ones that show us it's an impossible coincidence. We have to be looking at a Pythagorean relationship. There's just no way you could get these nice round whole values by coincidence, okay? They are much rounder, much nicer than the originals in W and D. And by the way, that's not only true in base 10, but also in base 60. If we were to go back to the base 60 representation of these numbers, that would really be true. Oh, that's right, I put that here, sorry. So almost all of these numbers are divisible by 60, the rest are divisible by 30 and by 12. 30 and 12 are very friendly numbers if you are a base 60 Babylonian. So not only are these numbers, nicer and rounder, they're really nice for a Babylonian. And that's kind of significant. That's pretty significant. We start to ask, what else did they know about triples and what mathematical meaning did they associate with those triples? And to explore that, we're going to start with, how did they get those triples? So here I've reorganized. So this is the two legs, W and L, the calculated value L, and then the diagonal, so they're in order from least to greatest. These are the triples from Plimpton 322. These are all the primitive Pythagorean triples under 100. So, 3, 4, and 5, 8, 15, 17. These are like the smallest Pythagorean triples. If one of us just sat down and I turned you loose on calculating, coming up with some Pythagorean triples, if I told you to fill out a table with 2 of 3 values, you would definitely start small, right? That's not what we see here. Those are quite large. Especially this one. This is 12,709, 13,500, 18,541. You would not, if you were just kind of guessing and checking or using an ad hoc method of calculating these values, there's pretty much no way you would arrive at some of these specific triples. So the author must have had some systematic way of generating triples. Again, there's just you just wouldn't come up with these off the top of your head. Now, there's a variety of theories for what mathematics the author may have had available. There are a number of formulas for creating Pythagorean triples. One of them we know from Euclid. So if you start with 2 integers, p and q, which are both integers, and the only restriction here is that p has to be the greater integer, then you can generate a triple using these formulas. That's kind of a useful thing, by the way. They may have known that and used that. It's potentially, and I think this was the theory favored by the scholars who originally translated and interpreted Plimpton 322 in the 40s, I think. More recent research, and that has sort of cross-referenced with the other mathematics that we know the Babylonians had and used, suggests that there might instead have been a concept called reciprocal ratios. The first column, the one that we did not translate, shows the ratio d squared over L squared. And in ABC language, that's the hypotenuse squared over one of the legs squared. That ratio, if you take the square root of that ratio, that kind of corresponds in terms of this formula to integers to generate this triple P and Q. So all this is to say, the first column showing the square of this ratio does suggest that that first column was filled out using specific values of P and Q in order to generate the ratio, and then later to generate the values in the triple. This is quite consistent with other mathematics that we know the Babylonians used. There's other documents from other tablets from the approximate era that show knowledge of this kind of math. Interestingly, there's a million patterns that kind of suggest this really might be what they used. But, we'll never know for certain. And there are other patterns that suggest even more theories about what they may have known. In preparing for this talk, I came across a really incredible one about complex numbers. There's kind of this is remarkable, very unlikely pattern that emerges when you apply a particular concept from complex analysis into those triples, which is wild. If you compute the value of the angle in the triangle that is defined by these, then you see a particular progression and pattern. So all this is to say, the Babylonians not only had awareness of the Pythagorean triples, they had kind of some deep knowledge about an underlying patterns, underlying formulas, the mathematics that you can use, not only to recognize and verify the Pythagorean triples, but to generate them. And the mathematics that they used, we might never know. So, okay, let's see here. I think I have 4 interesting things for us at this point. Something that to me is, at this point, it's a bit interesting, is that the Babylonians, they were aware. So we can conclude that. It's a bit interesting that we can conclude Babylonians were aware of Pythagorean triples long before Pythagoras. So as far as the question of who was first, definitely, Pythagoras was not the first. That's a bit interesting. It's a little more interesting to note that although the Babylonians did seem to be aware of a connection to geometry, they did not emphasize it or develop it in depth. That's a little more surprising. Quite interesting to me is that they not only knew about these triples and understood them, but they assigned them as math homework. That will never not be wonderful to me. The most fascinating thing is that the choice of triples in Plimpton 322 suggests quite deep knowledge of an underlying arithmetic relationship, possibly deeper than that of what the Greeks used later on, and some very sophisticated methods to systematically generate triples. The systematic nature is the interesting thing, that those values, are not the triples that any of us would come up with if we just sat down to fill out a table of 15 sets of triples. We'll end this section with just a couple, I think, nice quotes about Babylonian mathematics. And the first is, although we, this is one of the interpreters of the original interpreters of the tablet. Although we have an incomplete knowledge of Babylonian mathematics, there is one thing that we are certain of. We are dealing with a level of mathematical development which can reasonably be compared with the mathematics of maybe the early Renaissance. And then from Stilwell, the Pythagorean theorem was known in Babylon not only earlier, but understood better in Babylon than they ever were in Greece, at least until Diophantus. Diophantus in this period of 150 to 350 CE, that's almost, depending on where you count from, 700 years after Pythagoras. So, this question of who first can be answered, but also, there's this question of what mathematics did they use. They used something very rich that may not have reappeared until much later in history. So in closing, we're going to kind of recap and recontextualize the Pythagorean theorem, what we've developed here, in context of some of the tensions in mathematics. One of my goals at the start of this talk was to help illustrate, kind of with fresh eyes, what makes the Pythagorean theorem so incredible and kind of miraculous. as we outline that through these tensions, we are going to comment on kind of what it means to make meaning and also to share that meaning of mathematics. This is the same slide we saw before, so I'm just going to refresh your memory. The idea being that there is a tension, or at least, a disconnect between the domains of arithmetic and geometry. And if you were an ancient mathematician, the mathematics that the ancients produced were the linkages between these domains, because kind of at an a priori level, there's no real reason to expect that an arithmetic fact can be visualized geometrically or a geometric question can be answered by a calculation, right? If you're an ancient mathematician, these are separate. And mathematically, there's no intrinsic reason except for all the bridges between these two that have been discovered by mathematicians over the millennia. I like this quote, so we're going to look at it. There's a very different significance in math history of number theory and geometry. Number theory has been important in math, and perhaps more important from a foundational point of view. But number theory has always had glaring gaps because of just the darn intractability of elementary problems. Most of the old unsolved problems in math are very simple questions about the natural numbers, 1, 2, 3, and so on. So again, we can now come to the true meaning of the Pythagorean theorem. I defined this earlier as having a true meaning, that the Pythagorean theorem is the concept that arithmetic can be realized into geometry, and that geometry can be used to answer questions of arithmetics. And I hope by now you understand how shocking this is. The arithmetic relationship was understood in depth long before the geometric, and that the numeric calculation can inform the geometric and vice versa is just incredible. The Pythagorean theorem is the oldest connection between these domains. We're going to end with a little tour of how these ideas emerged in Greek mathematics. And what you should think of here is, although there is this bridge between these domains, this linkage, that bridge, let's see, I'm going to mix some metaphors. Was it a bridge over troubled waters? Was it a bridge to a dead end? Was it a bridge to conflict? Whatever. So to the Greeks were phenomenal geometers. In fact, very few new results about the plane figures have been found or proven since the days of the Greeks. They did do some number theory, but they did not do nearly as much as they did of geometry. For the Greeks, arithmetic was a huge source of conflict and controversy. The Babylonians, we think, they just weren't that interested in geometry. They just opted to focus elsewhere. But for the Greeks, this sort of asymmetry, more geometry than arithmetic, was because for them there were these enormous conflicts lurking within arithmetic. Many of us may be familiar with one of the most famous sort of very alarming discoveries that we attribute to the Pythagoreans. Using the Pythagorean theorem, again, this linkage, the notion that a geometric fact can be results as the realization of an arithmetic calculation. Doing so with this particular isosceles triangle, whose legs are 1, leads to a bizarre, if you're a Pythagorean, result. You calculate, 1 and 1 as the legs, then there's the square of the hypotenuse is 2. And then you start to write down this, c is equal to the square root of 2. If you were a Pythagorean, then you believed that all numbers could be expressed as ratios of other lengths. This is why this is where the term rational, irrational came from. Trying to express the square root of 2 in such a way will fail. You cannot do it. You cannot find ratios of other lengths to write down the value of this quantity. Can't be done. So the square root of 2 had no meaning as a number for the Pythagoreans. Just it didn't fit. They could not accept it as a number, but no one could deny that it was the diagonal of the unit square, of this triangle with legs 1 and 1. Those two things, on the one hand, that this as a number is nonsensical to a Pythagorean, and here it is, right in front of you, black and white and red. This was enormously upsetting and alarming for the Pythagoreans. And legend has it that the first Pythagorean to sort of publicly declare and try to accept that root 2 was a valid number, the first of what we now call irrational numbers, that Pythagorean is said to have been set adrift at sea. That's how alarming this was to them. Ultimately, these questions of how we make meaning of mathematics, they draw upon the history and the human element. The meaning of mathematics is not inevitable. So different cultures across time and place derive meaning in different ways, sometimes going further and other times, retreating in comparison to other civilizations. The meaning can arise from sort of cooperation and harmony. It can also arise from tensions and conflicts. Although this was, profoundly upsetting to the Pythagoreans and certainly a bummer for Hippasus, right? Ultimately, some of the efforts of the Pythagoreans to reconcile this nonsensical number with this unambiguous length ultimately gave us a lot of results which, although the Pythagoreans and the Greeks couldn't understand, later in history, that's what that means. And I think sharing sharing this meaning with learners is really important. It sparks curiosity and wonderment and wow moments. And if I were to define who is a mathematician, it would be a mathematician is someone who is just wowed by mathematics. Right? And so when we share these wow moments with our students, when we cultivate the conditions for them to feel amazed that they are doing the same homework as someone from 4,000 years ago, or that a theorem named for Pythagoras was known 1,000 years before his time, that kind of lets them experience being a mathematician too, even if that's like an 8th grade mathematician. So thank you for joining me. I have some, works and references for those who might be interested. Some of these are very academic, some are not. Thank you very much for joining, and I'd love to hear your questions.
Thank you, Claire. If you have any questions, feel free to unmute yourself, or you can use the raise hand function, or you're welcome to use the chat as well.
Okay, I'll start. The Greeks, you went into how the Greeks, well, the Pythagoreans had so much trouble with the square root of 2, but and Euclid was how much later? He was the one who actually proved, if I'm not mistaken, that root 2 is irrational.
Euclid, I think he was maybe 200 years later. One thing, one thing that's interesting is for the Greeks, the irrational numbers were this huge source of consternation. It's just this agonizing conflict to them. If we look at Hindu mathematics from India, they engaged with many of the same concepts. And solving equations, working with the Pythagorean theorem, the Euclidean division algorithm, and they did so encountering irrational numbers with no agony about it, right? So this thing about root 2 and irrationality is kind of unique to the Greeks, whether it's the Pythagoreans or Euclid, because other cultures did not have that conflict in their notions of length and of numerical quantity. Does that answer your question?
Yeah, no, I'm just saying that Euclid actually proved that root 2 existed and was irrational, as opposed to, he proved that it wasn't rational, which seems to be kind of beyond what we're willing to accept.
Even into the time of Euclid, a challenge with irrational numbers is that they for the Greeks, arithmetic and geometry were full of this conflict. Another conflict for Greek mathematics was infinity. And that was a really challenging, terrifying thing for them. And so one way this comes up in the irrationality of root 2 is in, expressing that value expressing the decimal representation, you tend to start writing out this infinite non-repeating thing. And so that kind of brought the Greeks, including Euclid, up to this concern about, infinity and infinite processes. And the Greeks used particularly the method of proportions and the method of exhaustion as ways to kind of get around, the sort of loop around and bypass the infinitude of those decimal representations and some other things. So even into the time of Euclid, there was, I think I agree with you otherwise, but there was still this conflict between length and quantity, and also just kind of an inability to really express that quantity meaningfully because of not only arithmetic and geometry, but also infinity. Great question. Thank you. Any others?
Since nobody seems to be asking anything, let's say one more thing about kind of related to that, because they were such geometers.
Mm-hmm.
They must have had an equal sort of a problem with the representation of pi, because they certainly were aware of the relationship between diameters and circumference.
Yes. Yeah, definitely. Yes, true. And one thing that we're running up into that's interesting is not only these sort of philosophical, existential questions of meaning making, but also like notationally, right? Writing, being able to write, where do I have it? Writing these numbers down symbolically. The Greeks didn't have this notation. So part of what they were aiming to do, this idea of expressing ratios of other lengths, some of that was related to, it was building upon the idea of how does measurement happen, right? Measurement happens by comparing to a known length, like think of a ruler, right? And so, wait, where was I going with this? Oh yeah, so they were, they didn't have this notation. To us, we can write this down, and it's sort of like a piece of fun trivia to say that the Greeks didn't understand this as a number, but they didn't have a way to write it down like this. They could sort of infer its existence. They could observe that it had to exist. It was clearly the length of the unit square, and it did, but in trying to measure it and trying to write it down, they ran up into these limitations of their system of notation, but also meaning making. Yeah. Jason.
Yes. So I'm curious. I've seen a whole bunch of work regarding to like these scribed texts that are often, I guess, copied or rote work.
Mm-hmm.
I'm curious, why does so much of that survive and not a whole bunch of like important textual or learning documents? Is there historical or cultural reasons that we have to infer these from this sort of work?
I like this question. Are you, just to reflect it back, are you asking like, we have a lot of tablets that are sort of copying, if this was copying, but not a lot that's in a school setting, that's more than copying?
That's my understanding, which could be completely wrong.
So I guess I'm inclined to say, firstly, I don't hugely know if you would call this copying, especially in light of the theories about how those triples were generated. I'm trying to get to the slide. Especially considering the first column, which I did not show you, I did not translate that. The first column, I think I think the total picture is that the author themselves was a scribe who themselves had learned this math. They're sitting down, they know they're going to teach the lesson on the subject, and they probably started with the P and Q values. So they had enough knowledge to draw upon, but then I think the theory is that this tablet is probably what they sat down to compute, right? So that when I'm sitting down to make a math worksheet, I know that I have to know enough to know what triples to pick. Maybe I have some prior knowledge, maybe I'm referencing some materials about them, but I'm sitting down and crunching the numbers myself. I'm in my notes that I'm preparing, I'm writing down my scratch work, right? Because I want to show that to my students or create a key or whatever. So I think probably I believe that we don't feel this tablet was just copied, like looking at a reference. One reason for that is from, so I took these slides out, but I'm gonna show them to you. So this is about the errors. So there's 4 errors, and they're really in, I think it's like 3 of the widths and 1 of the diagonal. Each of the errors is kind of arises from the act of creation versus copying. So there is a copying error in row 9 in column 2. Of course, remember column 2 resulted from column 1. So this is a copying from column 1. Then this I love, there's a squared value instead of the square root. This is just someone like forgot to keep going, right? And in the tablet, like makes it extra understandable, the squared value appears elsewhere in the calculation here. Not elsewhere as in being shown, but when you crunch the numbers, you will encounter it yourself. So probably this is the person actually calculating. This one I love, the diagonal, they divided by 2 instead of multiplying by 2. And so on. So I think the net idea is that probably this was created by a teacher as a teaching aid and not like copied itself from a reference manual, although the author had knowledge of that material in reference documents too. Does that answer your question?
Definitely an interesting answer.
Yeah, thank you. That was a great question. Do you have time for one more question or 2 or whatever? Yes, Chris.
Yeah, hi. I was wondering, could you go more into the base 60 of it all?
Yes.
Was there maybe something about that led to the generation of these numbers
Oh, I
easily?
love this is a great question. So, okay, thank you. So let's see, where's this slide? I have to find it. Aha. One idea related to one idea in support of the theory of reciprocal ratios has to do specifically with base 60 representations. Okay, so again, thinking about like how did the author choose these values? One fascinating thing is that for the values in Plimpton 322, the ratio d squared over l squared, and I think also the square root, just d over l, c over b, that ratio is either a whole number or it has a terminating decimal representation in base 60. So I've said decimal. The Babylonians had a concept of place value, including, just like we do. So, you go, not only ones, tens, hundreds, but also 1/10th, 1/100th, 1/1000th. The Babylonians had the same thing, except, 1/60th, 1/3600th, and so on. When you kind of fill in, when you crunch the numbers that would have been used in the reciprocal ratios derivation, you only encounter values that have a terminating representation in base 60. They want, Joel, wait, I'm trying to look here. They wanted an easy number, like for their students, right? This whole theory about this is a scholastic aid, a teaching aid, also has to do with, this very like relatable, like practical thing about wanting your students to get nice number answers. Anyone who's taught math with someone who has not yet learned all that much about rounding or irrationals or whatever, it's like that moment where someone goes, well, I got an answer, but it's like 7.413, and they read out 20 digits, right? And you go, okay. So all of the values that you get when you follow the steps of this theory, every one of them has a terminating sexagesimal representation. And so some of those are kind of clues related to how the author would have engaged with these numeric relationships related to their base 60 representation. Again, it's just so not only sort of this teacher's aid, but what math would they have used? They would have picked nice numbers, and but to specifically have to be nice in base 60. Does that answer your question?
Oh, yes, it does. Excellent.
Thank you. That was a great one. Any other questions?
Well, I don't want to cut anyone off, so if there's any last questions. Okay. Thank you so much, Claire, for sharing all about Pythagorean Theorem. Oh, and we have a visitor.
Yeah. Thank you everyone for joining. This was a really fun. Thank you.
Yep. We appreciate you guys coming to our second Curiosity Lab. This meeting's been recorded, so it will be posted on SSP's YouTube as well as the new networking SSPI network. And so if you're not part of the SSPI network yet, please, I'll have to drop the link in the chat, but please join because it's a nice networking slash social platform. And you can sign up as well as, so if you're interested in sharing something that you're passionate about, please, please let us know. And so I'll put my email at the bottom. Yes, there's a link for the network, and then here's my email if you have something that you're passionate about that you'd like to share. But thank you again, Claire, for taking the time to teach us all, and it was wonderful.
Thank you for having me. Thanks for everyone joining. Bye. See you guys next time.